What will make you know that a transformation of a system is a rotation or a picture? If I have a photograph or some image or some three-dimensional object, and I say, well, look, I do some movement of it to another configuration. What factors will make you agree that what I have just done is rotation? What will you look for? If I want to say, is this a rotation or is this not a rotation? What will you be looking for? What properties will you be looking for that will make you conclude that this thing is a rotation or it is not a rotation? Can you go to the chat room and tell me what will you see in a transformation of a picture or a figure, an image, an object, whatever you can see geometrically, graphically, that you will conclude that what has happened is that I have rotated it? What will make you agree that it is a rotation, and what will make you insist that it is not a rotation? Go to the chat room and tell me why you would say something is a rotation or why you say something is not a rotation. Okay. Okay. Patrick said change direction. Okay, same magnitude, different direction. It changes coordinates. Well, what if there are no coordinates? It's just a picture. If I just showed you a picture, I didn't discuss anything about coordinates, how would you know whether what I showed you later is the same as what you saw earlier, but it's just simply a rotation? I've had some good answers. I don't agree completely, you will see. And as I'm looking at all that the class has written, I will tell you something, same magnitude, different direction. Well, true. That's David Akinola. I am challenging the class because autonomous, well, something doesn't have to be autonomous to be a rotation. Origin the same. Well, the origin may not be the same. It may have some rotation and some translation. I want more answers because I'm going to give you a situation that fulfills all you have said, and it is still not a rotation. So, because the idea of a rotation is a very specific thing, and there are things that still fulfill all you have written, and it's still not a rotation. So I want to see if there are other things you will look for. And you will beat yourself when I give you this example. It will be an example that will be clear to you, and you will know it is not a rotation, but fulfills everything you have written so far. Try harder, class. Try and tell me what will make you think is this definitely a rotation and nothing else but a rotation. Change in axis and angle. When an object leaves a position and comes back to the same position, if it moves in a clockwise or anti-clockwise direction. I'll give you 1 more minute to tell me how you will know for sure that something is a rotation. Okay, I've given you enough time. Okay, if the object turns around, equation of rotation, no mathematics involved, just geometry. Don't bring math into it. Now, suppose I took your original object and put a mirror near it, and it gives you another object. will it not have the same, will it not fulfill all these things you have written, and it is still not a rotation? That one will be a reflection. A reflection is not a rotation. In a reflection, if it's a pure plane reflection, the size is still the same. The objects you can still see, they have changed in direction, but it's not a rotation. A reflection is different from a rotation. So the fact that the magnitudes haven't changed doesn't completely tell us it's a rotation. So at least you've tried. So but you know that one thing, for a rotation to take place, the magnitudes must be preserved, and the directions may change. But there is a particular kind of situation where that exists. I see not a rotation, and that kind of situation is called a reflection. There can be so when the magnitudes are preserved and the directions are changed, it could be a rotation, it could also be a reflection. Both transformations are said to be orthogonal transformations, but we will get to that later on. But I just want you to know that a rotation is not the only thing that can make magnitude remain the same, whereas the directions have changed. But you've tried. So let us go back to our class and then learn some new things today. So now, from this set of axes E1, E2, E3 to the set of axes Xi1, Xi2, and Xi3, we said in the two systems, the unit vectors are unit vectors, so the magnitudes haven't changed. The origins are the same, so they are in the same origin, and we are just dealing with a situation where we have just made some rotation from one to the other. We are going to now explain and show why that dyad that we showed earlier is called, well, this dyad EJ EJ dyad Xi J. What is it? It is a dyad because it is the dyad or tensor product of two vectors. It is a dyad product or a tensor product of two vectors. You remember, the other kinds of products are scalar or dot product, and then you have cross or vector product. This one is a dyad product. In the first one, you get scalars. In the second one, you get vectors. In the third one, you get tensor. And we defined the dyad by the way it behaves when it is operating on a vector. We'll go back to that shortly. Now, to see why this is a rotation, look at what it does to the vectors Xi j. J is equal to 1, 2, and 3. What I mean is Xi1, Xi2, Xi3. What I want to do now is I take the product at the head of this page 28, operate it on Xi1, get an answer. Operate it on Xi2, get an answer. Operate it on Xi3, get an answer. Just to remind me that you know what we learned last lecture. So take this quantity here, the quantity on top, operate it on Xi1, this quantity, operate it on Xi2, and operate it on Xi3. Let me find it. That is the first thing I want you to do. So if you operate it on Xi1, Xi2, and Xi3, tell me what the answers are. I'm going back to the chat room to wait for you to see what you have done. Operate the thing on Xi1, operate on Xi2, and operate on Xi3. Waiting for you in the chat room. Operate on Xi1. That is, let me put it for you. You take E1. Sadiq, you are wrong. Remember that J is repeated. So that quantity is a sum of three things. It's a sum of three things. So it's not just one thing. So you are multiplying a sum with E1, a sum with E2, a sum with E3. So there are three questions. There are three questions in one. You are multiplying the sum E1 Xi1 plus E2 Xi2 plus E3 Xi3. E1 circle times Xi1, E2 circle times Xi2, E2 circle times, you are multiplying that with E1, multiplying it with E2, multiplying it with E3. So that's what you are doing. So you must remember that our summation convention is active. I'm not having answers. Are the rest of the class sleeping? Did you get the question? Okay, let me go back to the question again. The question, what we are doing is this. Take this quantity here. Take this quantity, E. First of all, remember that this quantity is E1 circle times Xi1 plus E2 circle times Xi2 plus E3 circle times Xi3. You want to operate it on E1, you want to operate it on Xi1, on Xi2, on Xi3, one after the other, and see what the answer is. That is the first. This is the question here. The question, see what it does to the vectors Xi1, Xi2, and Xi3. What does it do to Xi1? Operate this quantity on Xi1. Remember the rule. Remember the rule of what remember what a dyad is. Remember the definition of a dyad. The dyad. Remember here that if you have a dyad, A circle times B operating on C is simply B dot C, which is a scalar, multiplied by A. This is the rule that you are going to be applying. So what happens here is that in each case, A is E1, B is Xi1, then B2, E2 Xi2, E3 Xi3, sum of all of them, operating on Xi1, for instance. Tell me what the answer is. Is that question clear now? You have EJ cycle times Ij, which creates a summation inside this bracket, and it's operating on Xi1. What is the answer? Work it out and tell me what the answer is. Patrick Oloko, you are in terrible error. You are in terrible error because when there is a repetition, what does it mean? It only means if you are using Z now instead of Xi, it's E1 Z1 plus E2 Z2 plus E3 Z3. That's all. The whole thing you are writing is nonsense. So if we use Z for Xi because we cannot type it, so it will be E1 Z1 plus E2 Z2 plus E3 Z3 with Z1. What does that mean? So that will be equal to E1 into Z1 dot Z1 plus E2 into Z2 dot Z1 plus E3 into Z3 dot Z1. What is that equal to? Then when you try that with each of the other ones, what is this equal to? What is Z1 dot Z1? What is Z2 dot Z2? If they are what is Z2 dot Z1? What is Z3 dot Z1? That's the question. You cannot see the slide because I'm at the chat room and because you are not making progress. I will show you the slide back again, but you can't see the slide because you are not answering me. I'm in the chat room trying to see your answers to the question. Yes, Patrick Oloko, you are getting, yes. Try Xi2 now and you tell me what the answer is. You are beginning to understand what's going on. Now try Xi2. Yes. Now try Xi3. Yes. So if you operate it on Xi1, you get E1. You operate it on Xi2, you get E2. You operate it on Xi3, you get E3. That is it. Caleb, what do you mean? What is E3? What did you use to get E3? What did you operate on to get E3? Yes, yes, but operate on Z1. What if you operate on Z1, what do you get? If you operate on Z2, what do you get? Good. So I want all that to have a feeling. No, no. When you operate on Z3, you get E3. Unless you have done something wrong. When you operate on Z2 or Z2, you get E2. I'm trying to get to a point. Yes. Patrick, you are doing okay. Caleb, you are now doing okay too. I want more people to get it. The others are still struggling. So let us take a look at the slides again and see how many people will follow. So see the question again. You take this quantity here, the quantity on top here, from current slide, this quantity on top here. Remember that it is a sum of E1 cycle times I1 plus E2 cycle times I2 plus E3 cycle times I3. That's what it is. If you operate it on Xi1, you get E1. If you operate it on Xi2, you get E2. If you operate it on Xi3, you get E3. Let us leave that. Let us go to the next question. That's the next paragraph, the next point here. It's transpose. Just reverse it. Reverse it now. If you reverse it, you now have Xij cycle times Ej. To prove that it's also a rotation, we are going to do two things. Let us see what it does to E1, E2, and E3. So operate this quantity now on E1 and see what the answer will be. And then operate it on E2, see what the answer will be. And operate it on E3, see what the answer will be. Go and show me those answers in the chat room. If you fail the first one, don't fail this one. Operate this new quantity, this quantity here in the third point. Operate this quantity on E1, operate it on E2, and operate it on E3 respectively, and tell me what you get. You can use Z instead of Xi to just make it easier for you to type. So you operate this quantity here on E1, this product. Operate it on E1, operate the same product on E2, operate the same product on E3, noting that this product is not just a simple product, it is a summation of products because of the repetition of the subscript J. I'm going to the chat room now to check what your answers are. Where is the chat room? Yes, Patrick Oloko, you are now in full flight. You can see it seems clear to you. I hope you can help your okay. Omoyola, yes, gives us Z1. Yes, you're correct. Yes, it gives us Z1, Z2, Z3. Yes, that's Z1, Z2, Z3. Good. Good. What are the others doing? Are they alive in class or are they sleeping? Kelechuku, good. Okay. Okay, so one more question before we move on. See the end of that question. What does it do to the vector? What does this second one now do to the vector 2e1 plus 3e2 minus 10e3? What does it do to the vector 2e1 plus 3e2 minus 10e3? That will take you some little more time to do, but I want you to do that and tell me what the result is. What does it do to 2e1 plus 3e2 minus 10e3? What does Xij circle times EJ. What does it do to 2E1 plus 3E2 minus 10E3? So I give you 3 minutes to get me that answer. Olashubumi, you are wrong. Khalid Ajayi, you are wrong. There's a difference between 2Z1, comma, 3Z2, comma, minus Z3. This, you look at the answer from Patrick Oko. Yes, Fabibi, you are now correct. Ohabuwa, you are now correct. So, okay. Okay, so, good now. Yes. If you go back, therefore, so what it means is that if there is a vector, what you have just showed is that if there is a vector in the blue system, it translates it to the same vector in the, what color is this now? Is it pink or whatever shade of brown it is? So it is a rotation. That I'm just showing you why we know that it is a rotation. Since the E1, E2, and E3, or Xi1, Xi2, Xi3 are unit vectors, you can see that the magnitudes of those vectors are completely unchanged. The only thing that has changed the vector is the orientation, because the axis that we are referring them to has changed. So what we have proved in all we have done is that this quantity here is a rotation vector, is a rotation tensor. Because whenever it operates on a vector, it just rotates it. That's all it does. It just rotates it. Whether it is a simple vector of coordinates or any other vector, what these things do, whether this dyad by itself or its transpose, they are both performing rotations. One rotates one way, the other one rotates the other way. So you see that if one rotates left, the other one will rotate right. If one rotates clockwise, the other one will rotate counterclockwise. So they are both rotation tensors or rotation dyads. So we are just beginning to see that is one thing. So this idea of a tensor product has very practical applications, and you will see that we are just starting. By the time we go further, you will see that they are not just, we didn't just bring these products out of a trivial idleness. It is something that is very useful in graphics and in animation and in simulation and many other things that you are going to look at for practical purposes. This example you have toyed with force you to this example forces you to really see how to work these things out. So let us move on. We are going to leave that briefly and go into something. We go into some other direction. We are going to look at coordinate system, and we will come back to the tensor thing or the dire thing shortly, but we first of all want to clarify some issues on coordinate system. Now, let us begin with the very familiar grounds of the Cartesian coordinate system. From secondary school, you are used to the XY system on a simple page of paper. When you go to the university, you now started talking about X, Y, and Z. That is a little bit difficult to draw because your paper is still two-dimensional. But with the computer, we don't have any problem drawing them. So the Cartesian system contains three autonomous unit vectors known as bases. The intersection of two planes creates a coordinate line. When two planes intersect, you have a coordinate line. For instance, what you call the x-axis, is actually the coinciding of the xy plane and the zx plane. That is what results in the x-axis. Let me repeat that. The x-axis is a way that the xy plane coincides with the zx plane. The xy plane coincides with the zx plane, that gives you the x-axis. What about the y-axis? And what about the z-axis? What planes coincide? So the intersection of two planes creates a coordinate line. The intersection of three planes creates three coordinate lines, all meeting at one point. So the intersection of three planes will create a point. And the point where they intersect gives you the location of that point. So when you say the point 1, 3, 4, you are saying that the positions where the planes x is equal to 1, y is equal to 3, and z is equal to 4, where they all coincide, that is what gives you your plane. For instance, the point I have here could be the point 1, 0, 0. If it is point 1, 0, 0, that means that x is equal to 1, which gives us the x plane, y is equal to 1, which gives us the y plane, and z is equal to 1, gives us the z plane. The plane z is equal to 1 is the xy plane, this one. And the plane y is equal to 1 will be the zx plane, and the plane z is equal to 1 will give us the x is equal to 1 will give us this plane. So that's how you get the coordinate system. If you have access to Mathematica, you can create these things yourself. You can create them on your own. This is the code with which I created the figure you just saw. But I'm not sure all of you have access to Mathematica. But if you did, this will just writing these 4 lines of code. We create the three intersecting planes. They are perpendicular planes and they all intersect at a point. The point where they will intersect is the point 1, 1, 1. Because in the first case, you have it around x is equal to 1. The second one, you have it around y is equal to 1. The third one, you have it around z is equal to 1. And the range of operation is between 0 and 1.4, 0 and 1.4, 0 and 1.4 in each of the 3 cases. That gives you around that point that we have that's of interest to us. Now, what I want you to do next, and here I want everybody to participate. I am watching it, and all the students that are just sleeping in class are not participating. Please change your ways, because it is not my joy to punish you for it. I think there are 2 things I want you to do. Each person, write the location of 10 points. We pretend as if you are in SS3 and you are in your further math class. And I'm saying, okay, on your XY coordinate system that you are used to, just give me 10 arbitrary points. The origin is 0, 0. You can have another point, -1, 2. And so just each person, just give me 10 points. Just write 10 points. Each person, just write 10 points. I'm going to go to the chat room and check you. Each person should just write 10 points. Okay, Michael, you wrote. No, just write them at once. Don't write them one by one. Michael Otegbola, just write 10 points. Just don't stop until you've written 5 minus 3. Yes, you are correct, but just write 10. Each person should write 10 points. I want to see the first person that will do it. Each person write me 10 points. Okay, Daniel, yes. Victory, yes. Patrick Oloko, yes. Yes. So each person writes in different points. Yes. That shows you are alive or you are awake. Yes. Adiola, yes. Khalid, yes. Please, I want more answers. There are 62 people in class. I want to see your answers. Just write those points. There's something I'm driving at. Just keep going. Now, time is up. So I want you to now do another thing. I want you to do another thing. So Edidion, Etop, I saw you. Now, I want you to do the same thing now for 3 dimensions. I want you to write 10 3-dimensional points. Write 10 3-dimensional points now. I've forgotten it. I've finished with 2 dimensions. Write 10 3D points. No, the way you are good. Victory or Habunwa, yes. 1, 2, good. No, Olua, Saba, you are late. We are now in 3 dimensions. We have left 2 dimensions. Sadiq, I saw you. Oloko, I can see you. Omoni, I can see you. Just 10 points. Good. Okay, that's good. So you know what so when I tell you a number of points, you know what I mean. And there are different points. No repeats. 10 unique points each. Okay, so the question is, what is a geometric point? So you know what a geometric point is, so much so that you can give me 10 in 2 dimensions, and you can also give me 10 in 3 dimensions. Now, each of you gave me a set of points. And let us now concentrate on the 3D points. I can call each set of values in your hand a point space. So each one gave me a point space, each one containing a set of 10 points. So when I call it a point space, what am I saying? When I say the 10 points you just gave me is a point space, what am I saying? I'm simply giving a name to the bunch of points you have just written down. I say the points you have just written down, I'm calling it Daniel Sadiq. I said that's Daniel Sadiq point space. Ohambo, I said that's Ohambo's point space. I can name whatever name you are, I can say that's your point space, which contains 10 points. And if I say, okay, locate them, if I give you enough time and 3 coordinate systems, you can actually put dots on those points. And that will be your point space. And each one of you have 10 each. That is it. So I can say what you have is a point space. If I collect all the points in a region of space, if I take a region of space, what do I mean by a region of space? I don't know where you are. Some of you are in the living room in your house. Some of you are in a classroom. Some of you are in the Dubbing Center near not too far from the dean's office, or sitting quietly on an easy chair somewhere. Just around you is a region of space. If I just take that region of space and I'm looking at all the points that are contained in them, if I collect all the points there, endow them with an origin and a coordinate system that is capable of geometrically locating each point, I have created a Euclidean point space. How do I create a Euclidean point space? I just located a set of points around me. If we were in a class now, I can say the content of our class. If I take a corner there, I say that's the origin. And I tell you this x-axis, this y-axis, this z-axis. What I have finished doing, I've created a Euclidean point space. And with that, I can, if I choose a proper kind of scale, I can say, give me point through 3, 2, 5, and you will locate it. Give me point 10, 8, 9, you will locate it. And everything can be located. And I can say that the desk that you are sitting on is located in this region of the space. I can take an edge of the desk and I can tell you what point it is at. I can take another edge. I can tell you what point it is at. That way, I can locate any object in space. That is very useful for a simple fact that every engineering item that you are interested in will be located in some kind of Euclidean point space. It doesn't matter what it is. If it's a motor vehicle, if it is a phone, if it is a beam, if it is a chair, if it is some equipment, if it is a photocopier, if it is a pen, it doesn't matter. If it's a human being, anything you can see. The only thing that may not be in the point space will be a spirit that you cannot really know. Because if it's a spirit, you don't know where, you cannot tell me what the location is. Okay, but if it is a physical object that we can handle, you can tell me precisely where it is located in the point space. We call that a Euclidean point space. How does a point space become a Euclidean point space? First of all, it contains a set of points, just like you have your 10 points. It can be an infinite set of points. The number of points may be uncountable, but it is a point space. We can make it a Euclidean point space if we have a way of referring to all the points. And what do we need to do? We create an origin and we create a set of coordinate axes. And to make that easy, let us say we are creating that using the Cartesian that we're already used to. We are going to move from the Cartesian system to non-Cartesian systems shortly. But let us first of all be very comfortable with the Cartesian system, because from the Cartesian system, we are going to take our flight and we are going to go to non-Cartesian systems. The whole purpose of this course, of this lecture today, is to introduce you to the non-Cartesian systems. All we have been doing so far, we are just been building the foundation. Please pay attention to the foundation, because when we take flight, you just suddenly see yourself in a completely different space that you are no longer used to, that is completely new to you. And what you will use to navigate yourself over there is your thorough base in the one you know. If you understand the one you know very well, it will be no problem to move on. But if you do not understand it very well, you are going to be struggling over there based on some problems that you had in the old. So your problem will not be the new one, will be that you didn't fully understand the old. So we can answer the question, what is a geometric point? You know what a 2D geometric point is. You know what a 3D geometric point is. You know that if you have a bunch of points, we can call that bunch of points a point space. And if we endow that point space with an origin and a set of coordinates, we can call it a Euclidean point space. Why the word Euclidean? Why do we bring Euclid, that has been dead for more than 3,000 years? Why do we bring it into all this conversation? We bring it into all the conversation because there is a kind of geometry that is due to Euclid. The geometry we do in engineering is Euclidean geometry. There are no Euclidean geometries, but the basic geometry we do is Euclidean geometry. There are harder geometries than that. That one is relevant to people who are going to space, but the geometry we do on Earth mostly is Euclidean geometry. A Euclidean point space is a space where you can do Euclidean geometry. The geometry that you learned in high school, that you are still doing, and we are still doing in engineering. Simple geometry, where the angles of a triangle are 180 degrees, where two where two lines, if they begin to be parallel, they will remain parallel, and so on. All the Euclidean postulates that you know are, that's why we call them the Euclidean point space. But we are going to move to other coordinate systems to represent the same. We are not going to leave the Euclidean point space. We are just going to look at other ways of representing the same Euclidean space. So let us make some general comments on the Euclidean point space. All engineering objects of our interest reside inside a form of Euclidean point space. You can always locate the points on these objects. This space contains point locations that can be occupied by a location in an object at a particular time. It is often of interest to be able to do several things. Number one, can we locate a point in an unambiguous way so that when I say this is point 387, all of us agree that it is point 387 and there is no argument. Okay? So if there's a way in which we can define the point in such a way that we all agree that we are saying the same thing, we are referring to the same point. Two, can we relate a point to one or more points in its vicinity? Can we say this is point A and point B is a point not too far from it? Because we may be interested in the line joining them, and we may be interested in the object between them, and we may be interested in what happens when the points move apart from each other. So those are the kinds of things. For instance, how can points move apart from each other? Let us say there is a bar that is one end is in point A, the other one is point B, and we use force to pull it apart. And we want to measure the change in length. That is one thing. So we are interested in what happened between point A and the original point B and when there is an increase. Those are the kinds of things that may be of interest to an engineer. Three, we may want to define quantities that take up values of interest at that point. Pay attention to that third thing. That is a very simple idea, but if you don't listen carefully, it becomes a problem for you. Define quantities that take up values of interest at that point. Wherever you are, suppose I gave you 500 thermometers, and you can place those thermometers at 500 different points and measure things, measure temperatures at those points. So I can ask you, the thermometer you put in point 381, what is the temperature it is reading? You tell me. Okay, what about the one in point 150, 0? You tell me. So that temperature is a value that you can get for each point. You can say it is a scalar point function. Why do we call it a scalar point function? It is a scalar value. Temperature is scalar. And it takes value from point to point. So it takes a value at one point, it takes another value at another point, and so on. So we can say that when I gave you 500 thermometers, you can give me the scalar point function of temperature at all the points in the particular region. Suppose it is not a thermometer I gave you. Suppose what I gave you is a velocity meter, and maybe wind is blowing, and the velocity at different points are giving different values. And say, okay, tell me the velocity at this point, tell me the velocity at this point, tell me the velocity, and you can tell me the velocity at each of those points. Then you can have a velocity point function or a vector point function, because a velocity is a vector. Or even another thing that could be of interest, those of you who watch TV a lot, you hear of the meteorologist who is telling you in the atmosphere there is some high pressure in one point, low pressure in another area. So if I gave you something to measure pressure, and you're able to position yourself in a large field, you can give me the pressure function at every point. You can tell, it's okay, the pressure at this, if I say, okay, what about point 1,000, 3,000, 10,000. Okay, you say this is the pressure there. So you can get a pressure function. You can, or suppose I scatter you on a set of fields, and what is important to me is the fertility on the field, or the wetness of the field, or the growth, the amount, or the height of the grass at a particular location. So you can measure that and also tell me point by point. You record a point and tell me what is there. Record another point, tell me what is there. Even if there are infinite points, you can plot a graph of it, or you can plot a surface of it and tell me what is there. All the things we have been talking about now have a name. We call them fields. So there was the first thing we discussed was a temperature field. When there is a function that is defined from one point to another, to another, to another, you call that function a field. So, example of fields, the temperature map is a field. If I give you 1,000 thermometers, the readings of those 1,000 thermometers based on the located at specific points is a field. The temperature, you can talk of temperature distribution, temperature field. You can also talk of velocity field. For instance, if you are looking at the flow of a river and over a rock, and you can see that sometimes the water bends to one direction, sometimes it is going straight, sometimes all those ones, even if the speed is the same, since the direction is different, the velocities are different. So you can have velocity field. Similarly, in a stressed material, you can have stresses and strains. Those are tensors. You can have scalar fields, you can have vector fields, you can have tensor fields. And all of these things are defined over the Euclidean point space. So you can see, if we have a Euclidean point space, we can express the Euclidean point space by noting the location of points. You were able to give me 10 points. What if I want 1,000 points? You will give me. If I want 1 million points, you will give me. If I define a region of space, the number of points there may be infinite. But that region of space contains can contain a field. If that is part of a beam that is loaded, at every point, stresses are defined, and those stresses give you the field of stresses in that region. So, we have talked about points, and we now want to talk about vectors. The Euclidean point space you have used our Cartesian coordinate system to describe contains points. They don't contain vectors, they contain points. It is critically important for you to be able to do graphics to note the distinction. You need to understand when you are talking about points as distinct from when you are talking about vectors. It is even more serious to note that the difference in order to do mechanical analysis, such as solid mechanics, fluid mechanics, thermodynamics, that our knowledge of continuum mechanics leads to. It's very serious to distinguish when you are talking about points. You can see that when you have a point, you can define a vector at a point. That doesn't make that point a vector. It just shows that there's a vector that is residing at that point. The point itself is still a point, but it can have a vector, it can have a scalar, it can have a tensor at that point. Just like temperature, velocity, stress, pressure, all those things can be defined. So let's move on. So look at this. If point O and P are points, let O be the origin. Drawing a line between O and P creates the vector OP. If you draw a line between O and P, a straight line, creates the vector OP, and it possesses all the attributes of vectors as we have previously defined. It has magnitude and it has direction. OP has magnitude and has direction. The magnitude is defined by the length of the line OP. The direction is defined by the direction of the line OP, and is sensed as from O to P. The vector we have just created is no ordinary vector. It was brought to life by joining the point P to the origin. It's not an ordinary vector. It's a particular vector. and it came to life. It came to life through 2 points. One is the origin, and the other one is an arbitrary point. It is called a position vector. Note that we could have created a vector by joining any 2 points. It is a no-brainer that every point in space can be treated as just we have treated P. Create a vector by simply joining the point to the origin. What you should know that it is just one way of creating a vector. That's not the only way to create a vector. It is just a specific way of creating a vector. After all, at point P, you could have had the velocity defined. You didn't need to join that to O. You can just measure the velocity of air flowing through that point. So there are many ways you can create vectors, but we are looking at a specific vector called position vectors. The vector created in this way has a name, and it is position vectors. We are emphasizing the fact that we have created a vector from a point by simply using a line to join the point to the origin. They are special vectors, and not all vectors are created in this way. So we are going to just look, before we go on break, we are just going to look at what happens when we create our position vector in a Cartesian system. Each coordinate surface is a plane. The 3 defined at a point are respectively parallel to the 3 you can define at any other point. Each coordinate line, the intersection of these 2 planes, are parallel to axes that are similarly parallel straight lines at all points. The basis vectors, usually defined as a unit vector along the axis, are always the same at any point in the Cartesian system. It doesn't matter where the point P is located. The basis vectors are the same unit vectors defined as I, J, and K, or E1, E2, and E3 along the coordinate lines or parallel to them, and they are always the same. There is no change. That gives you some fantastic properties. So, how do we get a position vector? A position vector is simply the linear function of the coordinates. So, you can say position vector R is simply x1 E1 plus x2 E2 plus x3 E3. You are used to that. We can easily write, so you can write that. Even if we have a vector field, a value defined there, you can say V is equal to, you can look at it in our 3 components. You can see the one on x-axis as a V1 E1, V2 E2, V3 E3, where V1, V2, and V3 are the components of the vector in the E1, E2, and E3 directions. There's no problem. Very easy. In order to find, say, acceleration or any other thing based on this, we can differentiate this function. And you have been differentiating this very easily. And when you are doing this differentiation, your teachers have always been very careful that you stay with Cartesian. Because if you don't stay with Cartesian, you are going to get into trouble. And we are going to navigate those troubles in the next hour. Because if you want to differentiate, you forget about E1, E2, and E3, because you know that E1, E2, and E3 are always constants in the Cartesian system. So when you differentiate, you only differentiate the coefficients. Since E1, E2, and E3 are themselves constants, we need to worry only about the components, as their vector bases are all constants, always constant, and nothing but constants. These nice features occur only in the Cartesian system of coordinates. That is something you should put your finger on. It is this thing you have been doing, this free booze you have been drinking. You can only do that when you are in Cartesian system. We are now going to move away from Cartesian system, and now how are you going to survive? For example, there is something that we always work. Suppose I take a partial derivative of R with respect to x1, I take it with respect to x2, I take it with respect to x3. Do you agree with me, class, that if I differentiate R in this equation, if I differentiate this R, let me put this in very well. If I differentiate this R in this equation with respect to x1, do you agree with me I get E1? If I partially differentiate R with respect to x1, do you agree? Or have you not done partial differentiation yet? Let me just check. Let me ask the class. Please answer me in the chat room, so that I'm not just talking to myself. Have you done partial differentiation? Okay, you have. Thank God. So we can move on. Okay. So do you agree that if we differentiate partially, we differentiate this equation partially with respect to x1, we will get E1. If you differentiate the equation partially with respect to x2, we will get E2. If you differentiate partially with respect to E3, we'll get x3, we'll get E3. So if we differentiate partially with respect to xi, we're going to get EI. Do you agree with that? Okay, you agree that if we do those differentiations, that's what we'll get. Good. I want to draw your attention to a very deep result, which looks so easy, but this result we are seeing here is something that applies to Cartesian system, but applies to every system, whether Cartesian or not. That if you differentiate partially with respect to the coordinate axis, you are going to receive the basis vectors. It doesn't matter whether the basis vectors are variable or they are constant. So we are going to utilize this simple result, and we are going to get things that you couldn't have gotten any other way. The partial derivative of the position vector to the three coordinate variables constitute a set of linearly independent vectors that can form the basis set. In the Cartesian system, they are the same as our usual basis set. So you can see they are E1, E2, E3. This thing we have just done, we are going to use it whether we are in cylindrical coordinates, whether we are in spherical coordinates, whether we are in confocal elliptical coordinates, whether we are in oblate spheroidal coordinates, whichever coordinate system, that even systems that have not yet been created. If you differentiate the position vector with respect to the coordinate axis, you are going to get the unit vector. You are going to get the basis vectors you are looking for. That is how we will find our basis vectors, and it will always work. So this simple definition is going to carry on. To form a coordinate system, okay, so we are going to now move into the Cartesian system is a linear coordinate system. We are going to go into non-linear coordinate system, and we are going to use the example of the cylindrical and spherical, and that will be the topic from after the break. And because we have spent a lot of time here, I'm going to give you 15 minutes break. So meet me again at 11:20. 11:20. It's 11:20. Let's go. The Cartesian system you are used to is a linear system of coordinates. Cylindrical coordinates, spherical coordinates are non-linear. You will see why they are non-linear shortly. And you will see some things that you've been taking for granted that you can no longer take for granted, and you will need to put them into consideration, bring them into consideration in order for you to function effectively outside your outside the comfort zone of Cartesian coordinates. One of the things you will discover is that the unit vectors, the coordinate vectors, the basis vectors are no longer constants. They are variable, just like the coefficients are variable, the vectors themselves are variable. They are not pointing in the same direction all the time. They point in different directions depending on where you are. So when you want to differentiate, you have to differentiate not only the coefficient, you must differentiate the vectors themselves. So you need to know what the derivatives of the vectors themselves are. And we will begin by generalizing the way you form a coordinate system. How do you form a coordinate system? You can form a coordinate system by just selecting three variables and give meaning to the variables. Let us say they are xi1, xi2, and xi3, just like you chose x, y, and z. It's just the meaning you gave them that make them Cartesian. When each takes a value, xi I is equal to alpha I, like this, if x is equal to 2, y is equal to 1, and z is equal to -10, you say you are at point 2, 4, -10. That is all. But what do those points mean? Where each alpha I is a real number, then we have the point alpha 1, alpha 2, alpha 3. We can write this point in at least two other ways. We can write xi I is equal to alpha I, or as xi1 is equal to alpha 1, xi2 is equal to alpha 2, xi3 is equal to alpha 3. For each xi I is equal to alpha I, we have defined a coordinate surface. In the case of Cartesian coordinates, given any three alpha i's, we have x1 is equal to alpha 1, defining a plane with normal along E1 axis. Alpha x2 is equal to alpha 2, defining a plane with normal along the E2 axis. And x3 is equal to alpha 3, which is a plane with normal along the E3 axis. So the case of Cartesian coordinates, each of these fixed values of x, y, and z, or xi1, xi2, xi3, each value we have give us surfaces which are planes. When you get to the other coordinate system, they are no longer planes. They are different things. Some of them may be planes, they may not be planes. So you have to be very careful because they do not follow your Cartesian system. We would go through how specific choices lead us to cylindrical polar or spherical polar. We will show how we will do that. And we'll concentrate on those two. When we master them, in the exercises, we will look at other systems. But once you understand how to form the cylindrical, the spherical polar, how to operate with them, you see that you can operate with any system of coordinates, no matter how it's defined. The rules are the same because they are all non-linear. Let us move to the cylindrical polar in two steps. We introduce a transformation called the polar transformation. It's something you already know, such that x1, which is our x-axis, is simply r cos phi. x2 is simply r sine phi. Note also that this transformation is invertible. Just like you can get the x1 and x2 from the r's and thetas, so also can you get the r's and thetas from your x1 and x2. For instance, it is invertible because the r is simply the square root of x1 squared plus x2 squared, while the phi is the angle whose tangent is x2 over x1. With such a transformation, we can locate any point in the three-dimensional space with scalars xi1, xi2, and xi3 are now r, phi, and z instead of our previous x1, x2, x3. So you are now dealing with r, phi, and z. So if I tell you, give me 10 points, you are going to tell me the r value, the phi value, and the z value. Before we move on, notice that there is already a fundamental distinction between this coordinate system and the Cartesian we are used to. First of all, note that in the Cartesian, x1, x2, and x3 are all referring to lengths. Length in the x1 direction, length in the x2 direction, length in the x3 direction. Whereas when you get to the cylindrical polar, the r is a distance from a pole. That's the length. The phi is an angle, which is dimensionless. And z is a distance from a base plane. So you have three things that are not in the same units. Because these three things are not in the same units, it's going to give you some problems that you will see ahead. And if you are not careful, you cannot just do what you are doing with Cartesian, where everything is length. Here, some things are length, some things are not. So at least the angle in between is an angle, it's not a length. That has some implications, as we will see. So what does the position vector look like? To form a position vector in the cylindrical polar coordinates, The easiest way is to start from the Cartesian. Not that you can't do it directly, but if you do it directly, you may go into error. Let's start from, because the position vector in the cylindrical must be the same position vector we got in the Cartesian. They must be equal, because the coordinate system you use, the position vector is a physical quantity and it is independent of coordinate system. So if it has a value in one coordinate system, that value must be equal to the value it has in another coordinate system. So what we do is that you remember that x1 is simply r cos phi, and x2 is simply r sin phi. So in this expression, and z is the same thing as x3. So we have just started from here, and we have written exactly the system in the Cartesian here. So we can write this third equation that it is the same thing as RER plus ZEZ. If we define ER as cos phi E1 and sin phi E2, and EZ is E3. So you can see that the position vector in the spherical, in the cylindrical, does not even have anything to do with phi. Where did the phi go? The phi vanished into thin air. Some sort of. See, you just have R, you just have RER plus ZEZ. Don't worry, you will see where the phi is hiding somewhere. We will bring it out shortly. But remember, we said before that if you want to get the basis vectors, you just differentiate with respect to the coordinate variables. So what happens if we differentiate the position vector with the coordinate r? It is regrettable that we're using two r's here. There's an r vector and there's an r scalar, and they are not directly related. And I should have used a big R here to make sure that the confusion is, but don't worry. Let us just take this first equation, that is the first thing here and the last thing here. So if you differentiate this with respect to R, what do you have? You differentiate this with respect to R partially. The only thing remaining is simply ER, which is cos phi E1 plus sin phi E2, which is what we call ER. What if we differentiate it with respect to phi? If you differentiate, can this thing be differentiated with respect to phi? Phi is not occurring explicitly here, but it is occurring explicitly if we write the ER out explicitly. If we differentiate it with respect to phi, writing the phi there explicitly, you will see that this, if we differentiate it with respect to phi, what do we have here? We have R will survive, and the ER will be minus sin phi E1, and then the second one will be R that is multiplying here plus cos phi E2. If we write that, if we define that as R E phi, it then means that E phi will simply be, the E phi will simply be minus sin phi E1 plus cos phi E2. So that means that this R E phi. That is the interesting thing. The interesting thing is that if you look at this expression where it doesn't appear that phi is occurring there, you can still differentiate with respect to phi because the ER itself is a function of phi. So because ER is a function of phi, it is possible to differentiate this with respect to phi. So you can see now with the derivative with respect to R, with respect to phi, with respect to Z. With respect to Z, you just have EZ on both cases. If you differentiate with respect to R, you have ER. If you differentiate with respect to phi, you have R E phi. You have R multiplied by E phi. Because if you do not multiply it by R, E phi alone by itself is going to give you no measurement dimension. So you multiply it by R. So that is what, and it comes out, everything just comes out neatly by taking the partial derivative. So the partial derivatives with respect to the coordinate systems give you the basis vectors directly without, so you can just depend on partial derivatives. Whether the basis vectors are appearing explicitly or not, partial derivatives will give you the basis vectors directly, even if the position vector does not seem to have it explicitly. So that is what you have here. You can now check, you can check the magnitudes of ER, E phi, and EZ. ER, the magnitude of ER is simply 1, the magnitude of E phi is simply 1, and the magnitude of EZ is simply 1. So they are individually normalized, with each having a norm or magnitude of 1. Let us now take them in pairs. Let us take the dot product of ER and E phi. If you take the dot product of ER and E phi, you'll find it is 0. If you take the dot product of E phi and EZ, it is 0. If you take the dot product of EZ and ER, it's also 0. So they are individually normalized and pairwise orthogonal. So that means that they form an autonomous system. And that autonomality does not matter what the angle phi is. Whether the thing is changing with respect to phi or not, they are always permanently autonomous. It does not matter what directions they are facing. They are always autonomous. It's an autonomous system. And then, if you know how to use Mathematica, you can launch these three. If you launch these 3 commands, you are going to get this. These are the coordinate planes. The coordinate planes, the R plane is this. When R is constant, you have a cylinder like this. And when theta is constant, you have a plane that is cutting it. And when Z is constant, you have a base plane that is slicing it. And you will see that where those 3 meet is always at right angles. It does not matter the orientation of phi. They will always be at right angles to each other, and each of the coordinate lines are equal. So I advise those of you who have access to Mathematica, you can do this yourself. Use this, and you generate. I generated this picture with this code. So you just type the code in, and you'll get this picture. Now, let us look at the mistakes to avoid. The mistakes to avoid. If you were to follow the Cartesian system, and somebody asked you, what is a cylindrical position vector? You will think that it is RER plus phi E phi plus Z EZ. You realize that this is a simplistic copy of the Cartesian formula. It is wrong in at least 2 ways. For one thing, it is dimensionally incorrect because the unit of the middle basis component is an angle, while the other components are measuring lengths. See, you cannot add if the unit vectors are having the magnitude of 1 and they are dimensionless. So you have what is multiplying it here is a length. What is multiplying it here is a length. What is multiplying it here is an angle. Can you add angles to length? Of course not. So this is not possible. This middle term is not possible. In fact, the middle term does not even exist as part of the position vector. If you go back to what we have done, you see that it does not appear in the value of the position vector. So a simplistic copy of the Cartesian formula errs. Secondly, we cannot obtain the Cartesian result from this via a coordinate transformation. So this quantity is wrong. The another thing you also need to be weary about is that you may be thinking that basis vectors are constants. They are not. The ER is a function of phi, the E phi is a function of phi, and it's only EZ is a constant. So you have 3 basis vectors in the Cartesian, in the cylindrical. Only one of them is constant, like in the Cartesian case. The other 2 are functions of phi. So you will notice when you are cylindrical, when you go in one particular direction of your R, if you get another thing, it's going to go into another particular direction because it depends on the value of phi. So if phi is pi over 2 is a different direction. If phi is pi is a different direction. If phi is 0, it's all different directions. So The ER and E phi are not constants. They are varying with respect to phi. So only EZ is constant, like in the Cartesian case. Well, let us now use the rest of our time and move into the spherical system. We've finished with the Cartesian system. To move to the spherical system, we begin from instead of beginning from the Cartesian, we begin from the cylindrical. So we transform the cylindrical from Rz to rho theta. So we have a relationship because since the position vector in the cylindrical is RER and ZEZ, we are introducing a relationship that R is equal to rho sine theta and Z is equal to rho cos theta. And if that is the case, if R is rho sine theta and Z is rho cos theta as before, we can use three scalars rho, theta, and phi. We are using three scalars rho, theta, and phi instead of the R, phi, and Z. In comparison to the original Cartesian system we begin with, we have that R is equal to xi plus yj plus zk, and it will be rho sine theta er plus rho cos theta ez. But you remember what er is. Er is cos phi I plus sine phi j. I just want to write it in a more familiar term. And then we just use k. For now, let's just use the ijk that we are used to. So if we do that, we'll see that R is simply rho sine theta cos phi I plus rho sine theta sine phi j plus rho cos theta k. If you put all of that together, you can say it is equal to rho e rho, and e rho now is a function of theta and phi, where e rho is sine theta cos phi I plus sine theta sine phi j plus cos theta k. Is a nonlinear function of the coordinate variables rho, theta, and phi. It's nonlinear because it has these transcendental functions sine and cosine, so it cannot be linear. So it's nonlinear in rho, theta, and phi. If you want a physical show of it, that is what you have here. So if theta is the angle between the plane of interest and the original plane, so if phi is that angle, and theta is the angle between the vertical axis and the point in question, and then rho is the distance from the origin to the point. So you just have now that your E rho is radiating outwards, E phi is the tangent to that to that latitudinal line there, and E theta is the tangent to the longitudinal disk there. So that's what you have, and the relationship between R and the rho is what you have here. This is something that you have to sit down with after class. It's not something you can memorize in class. It's something you have to sit down and understand after class. But what is clear here is that the position vector, the unit vector here is a function of rho, is a function of theta and phi. And this is the full thing for E rho. Then the question is, what is E theta and E phi? Easy. Very easy. First of all, notice that the position vector here has only a single term. From this single term of position vector, how can you now find the three basis vectors? Very easy. Just differentiate R with respect to rho. If you differentiate R with respect to rho, you see that you get E rho. Partially with respect to rho, you get E rho, which is your first basis vector. If you want to get the second one, differentiate with respect to theta. If you want to get the third one, differentiate with respect to phi. That's it. That derivative, that differentiation method will always produce for you your basis vectors. So again, we introduce the unit vector E theta is this and retain E phi to be this. As before, it is easy to demonstrate the fact that these vectors constitute another autonomous set. Combining the two transformations, we can move from XYZ system of coordinates to rho phi theta directly by transformation equations. X is equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. The autonomous set of bases, of bases for the rho theta phi system is E rho, which is a function of theta and phi, E theta, which is a function of theta and phi, and E phi, which is a function of phi only. So you can see that two of them are angles, and only one of them is in length. So that is it. And you can obtain the remaining two just by simple differentiation with respect to theta and phi. So try that differentiation. The differentiation is a little bit, if you differentiate the first one with respect, if you differentiate the position vector with respect to theta, you get the second coordinate. If you differentiate with respect to phi, you get the third coordinate. So you do those differentiation and you'll be home free. It is 11:42. We still have 8 minutes before the end of our class. I'm going to give you 5 minutes to go to the chat room and ask me any specific question. If there's anything you want me to repeat or you want me to talk about and you think you do not fully understand, I should say more about it, please go to the chat room and let me meet you there. Waiting for questions. Okay, Ogunwolu is asking, why do we need nonlinear coordinate systems? There are problems that are of interest to us that can only easily be defined in the cylindrical coordinates. For instance, if you are working with pipes, to be referring in a pipe, the circle is simply Z is equal to A. That is the equation of a circle. Compared to x minus something squared plus y minus something squared is equal plus z minus something squared is equal to r squared. So the equations become very complicated when you are using Cartesian. So there are certain problems that the Cartesian systems are not useful for. They are not good at all. So you have to use cylindrical, and then when you are looking at point forces, the spherical system is the simplest way. So there are reasons why you do not use Cartesian in certain situations. Is there any relationship between polar form in vector and cylindrical polar that allows us to navigate? That's precisely what we are doing now. We are showing how to transform from one coordinate system to the other. So even if you have equations in one form, you can always transform them to another. That is the whole idea. That is why you are understanding how the unit vectors are formed. Once you know how the unit vectors are formed, you will find later that any system of equations you have can always be expressed in another form. You can have an set of equations in Cartesian and change it to spherical and change it to cylindrical and vice versa. So the whole idea is that you should be able to navigate between one or the other so that you can use the simplest method. But just know that once you move to the nonlinear systems, the unit vectors are no longer constants. And when you are no longer able to just differentiate the coefficient and know that every other thing is okay. So that is just the issue. And that is not as hard as a problem as it might seem at first. There are problems that are much harder than that. Somebody, VO Victory or Habua, wants me to re-explain page 47. So I don't even know what page 47 is. Let me go to page 47 and take a look. So there's nothing in page 47. All you do is you remember that the first equation is Cartesian. The second one starts from cylindrical and use the transformation from cylindrical. You remember that in the previous page, let's just see. You remember in the previous page, you remember here, we said the transformation from cylindrical to spherical is R is equal to rho sine theta, Z is equal to rho cos theta. That's all. So that where R used to be, you write rho sine theta, and where Z used to be, you write rho cos theta, because that's the transformation equation between the cylindrical and the spherical. And then you remember that ER, when we were moving from Cartesian, this in bracket is ER. We said it's cos phi E1 plus sine phi E2. So E1 is I and E2 is J. And then that's it. So that's all so here you start with Cartesian, here you use spherical, here you converted from you converted ER and EZ to their Cartesian forms. And then here you open the brackets. After opening the brackets, and you now say this whole expression is rho, E rho of theta and phi, where E rho is sine theta. Just like that. This page is straightforward, and there is nothing, really nothing there. And everything that is happening here is shown pictorially there. All the values, I did this drawing here to show you all that's going on here. So you can just take a look at it again in your quiet time, and then you should be okay. So let's see whether there's any other question. Okay, so that's it. So that's it. There's nothing really on page 47. Is very easy, very well explained. I will give you 1 more minute. There's no question after 1 minute. I will tell the any other question for 1 minute. I can spend more than 1 minute if you give me another question, but if there's no other question after 1 minute, please, okay. Is mathematical programming compulsory? Mathematical programming is not compulsory, but if you can do it, it makes life easy for you. So anybody, for instance, if you can do, many times I get my diagrams. I get my diagrams by programming in Mathematica. And those diagrams are quite illustrative. If you can do Mathematica, you can do the same thing yourself, and you can get better illustrations for yourself. That's all. If the question Chukwa Hache, what Chukwa Hache is asking me is like asking me, if you go to China, is it compulsory you can speak Chinese? Of course, it's not compulsory. But when you cannot speak Chinese, you are inside the bus, they are laughing at you, and you are laughing with them because you don't know that it's you they are laughing at. You see a sign that tells you that there are crocodiles on the road, and you continue going because you didn't read it correctly, and you get eaten up by crocodiles. That's all. If you don't mind being eaten up by crocodiles, there's no need to learn Chinese when you're in China. So if you do not mind being eaten up by the crocodiles of this course, there is no reason for you to learn Mathematica. It's just that you can get eaten up by the crocodiles of this course. That's all. If you don't mind that, no problem. So Chukwa Ache, I hope I've answered your question very well. Mathematical program is not compulsory. But know that you can survive in China without knowing Chinese. You can go to Libya or United Arab Emirates. You don't know how to speak Arabic. It's good for you. You will only speak to those people who can speak English. But somebody who can speak Arabic is going to navigate that place much better than you. So if you can use Mathematica, you are going to navigate this course much better than somebody who cannot. So that's just the truth. It is not, there's nothing I can do about that. I will keep supplying the mathematical code whenever I use Mathematica. So those who know it, use it. Those who don't know it, that's okay. We will still talk to you, no problem. But I don't have any other way of drawing my, for instance, just imagine those, the coordinate planes of this cylindrical coordinates. I don't know how else I can get it without Mathematica that neatly. You can do it manually, but I prefer to do it programmatically. That is easier for me to operate that way. So apparently, there are no other questions. So what I will tell the class is, please go through the notes again. If you have difficulties with any part, at the end of this course, where can I apply the knowledge learned? You cannot apply the knowledge learned unless we have a subsequent course. This whole course is to just give you the background for your continuum mechanics. We are just warming up. We have not even started the background, because what I've done so far is to review your vector analysis from secondary school to the first 2 years in university. I try to review what you were when you are pretending you are learning vectors. I just try to summarize all that there is to it. Then just showed you a little bit more vector analysis in order to bring you to tensor analysis. When we now do tensor algebra and tensor calculus, from there we can now do kinematics. From there we can now start learning continuum mechanics. You cannot even get near it. You are still at very, 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 very elementary level. So the idea of where would you apply this does not even arise. You are like somebody who in primary one, and they are telling you, do 1, 2, 3. Say 1, 2, 3, 4, 5, 6, 7. Excuse me, sir. Where do I apply this knowledge that I'm learning? You have not started learning. You are just still doing preamble. We are still in preamble, my dear Mr. Emmanuel Adeneko. So just sit down and learn your 1, 2, 3 very well. And let us clap for you that you are learning it. Because if you have a download of my book, which is supposed to be for 2 or 3 courses, then you will see that you cannot even go to the middle of that book without mastering these preambles. The preamble you are learning is still in the first part of chapter 1. It's still in the first part of chapter 1. We have not even finished chapter 1. And then, so that's the thing. So you have not learned much, but you have learned something. It's small. You have learned something, but where you will apply it, you apply it in continuum mechanics. And the continuum mechanics is the most of the mechanics courses in engineering is continuum mechanics. Whether it's fluid, you can now learn things like fluid mechanics, thermodynamics, and all those ones at advanced level. And that is what most of your physical engineering courses are all about. So that is my answer to you. But just still learn something first before you start. Finish your 1, 2, 3 and ABCD before you start knowing. If just imagine somebody answering a primary 1 child who is saying this ABCD and 1, 2, 3 we are learning. Where are we going to apply it? What are you going to tell that person? You just tell the person, go and learn your 1, 2, 3, Bo. That's all. Finish learning it first and then master it. Then you will now know where to apply it. If you don't master it, then the issue of applying it does not arise. So I think there have not been any new. I hope I've answered. If there's anybody whose question I've not answered, please repeat it or draw my attention. I think I've answered every question that I can see. And it's already 11:56. And we're already exceeding our time. So I wish all of you a very good day. So till next week. Bye.